we are very happy.
Recording in progress.
Andrej Bogdanov here today. So he's moved to the University of Ottawa as a professor since 2023, right? And before that, he was in Hong Kong, Chinese University of Hong Kong for many years. And before that, he was a postdoc in Tsinghua, IAS, and DIMAX. And then he was a student in UC Berkeley with Luca Trevisan. So his research is in complexity, cryptography, and randomness in computation. Right? He has done a lot of other stuff. So, yeah.
Thanks, Lapchi. It's a pleasure to visit. Great department to visit. And well, I have a confession. I'm going to, like, lately I have found that it's much more fun to talk about topics that I don't know much about, because you know, then you learn more things. But there is a risk every once in a while that you talk to an audience that actually does know about the thing. So, well, here I go. I'll have to take that risk today. And you know, and the other risk is that I don't have that much to say. But you know, nobody minds going home early. So now that I have set low expectations, I feel like I can start. So I want to talk about some recent work I did on estimating the Euclidean distance of a function to linearity. And this is a joint work with Lorenzo Tashin, who was a master's student. The motivation for this is, you know, regression is one of the kind of main algorithms that is used in computer science and in statistics and in machine learning. So what is regression is that you get a bunch of samples where you have of the form x f of x, so x is some input, and then f of x is the value of some unknown function on this input. And the objective of regression is, after you have seen like enough of this kind of data, that you want to find some kind of approximation to this function, and specifically you want to come up with a linear approximation. And the great thing, you know, there are many great things about this algorithm, which is why it's so useful. But you know, one of the nice things about it is that, you know, it's an algorithm that you can try. Like, you can try it on any data, and it's guaranteed to give you something, right? So recently I taught this course in algorithms, and I kind of realized there are two types of algorithms. There are algorithms that you can try, and there are algorithms that, you know, like you have no idea what they're going to do. And this is one of these that you can try, and it's guaranteed to actually, you know, given that you have sufficiently much, sufficient amount of data, to output, like, maybe not a very good approximation, but to output the best possible linear approximation to the function that you want. And how do you measure the quality of the approximation? And you know, there is a lot of discussion for that, but for the purpose of this talk, like, the quality of the approximation is, we assume x comes from some distribution, and we want to say what is the error of the best linear approximation is the average square distance averaged over the inputs. Okay, so that's the motivation. And now, since regression is so important, like, another reason it's good is because it's fast. But you know, you run it on bigger and bigger and bigger data, and you might ask the question, you know, like, before I bother running it, like, can I get some idea of like how good I expect the approximation to be? And that's kind of the motivation for this talk, is that can we do estimation of the best linear approximation faster than we can do the task of learning the best linear approximation? And I said it's going to be a short talk, so let me cut to the chase right away. So we give a theoretical yes answer to this question. So let me explain to you sort of what the answer is and why maybe it's not what you want, but it's what I'm going to talk about. So how are you going to answer this question? Well, you need some kind of model. And the model that we look at in today's talk is that we're going to assume that f is a Boolean function, so the domain is the Boolean cube, and it takes real values. And this is the assumption that makes it like somewhat unrealistic, is that I'm going to assume that the distribution over the inputs is going to be the uniform distribution. Why is it not terribly realistic? Is because much of the utility of regression comes from the fact that you can run it under arbitrary distribution, and it always does very well. But I want to kind of convince you that, well, you know, we have to start somewhere, and for the purposes of kind of understanding the theoretical distinctions between learning and estimating functions, well, the uniform distribution is kind of a natural starting point. So what I want to talk about today is this, that it's actually easier to estimate than to learn. And then, like, what is the model in which we prove easiness and hardness? So we can think about two possible kind of reasonable models. One is a query complexity. So in the query model, you're given the function f as some oracle in the sky, and then you can query it at arbitrary inputs and get the value of the output at this point. And you can also ask about it what happens in the sample model. So if I get uniform samples from the distribution, then just random samples from the uniform distribution, then what can you do? So the main thing I want to talk about today is that its estimation is actually easier than learning in both of these models. And so let me show you what the results are. So we can look at the estimation problem and the learning problem, and we can look at it in the query model and in the samplers model. And I'm mostly going to be interested in the query model in this talk because that's kind of where I find the theoretical results the most interesting and maybe the most surprising. So if I want to learn a function on n inputs, learn a linear approximation of a function on n inputs, I would expect that the amount of queries I have to do should depend on n in some way, right? Because just to write down the function, I have a function on n variables. I would need something that depends on n. And in fact, there are algorithms for doing it, and there is the algorithm of lineal Mansur and Nissan for the uniform distribution that actually learns it using n divided by epsilon queries. So what are the two parameters here? N is the dimension, and epsilon is the quality of the approximation, the quality in terms of the squared L2 distance between the function that I'm trying to learn and the closest linear function. So the LMN algorithms learns it using n over epsilon queries, and the main kind of insight, or I'd say kind of what I find somewhat surprising is that if I want to estimate it, then the dependence on n disappears. So I can estimate the distance to the closest linear function using roughly just 1 over epsilon squared queries. So that's the main result. Sort of we also have some matching lower bounds, which if I have time maybe I'll tell you about. Is that again, it's not terribly surprising that you have a linear dependence on n when you're trying to learn. So there is a little bit of suboptimality. The upper bound is epsilon and the lower bound is square root of epsilon. So this one is in the query model is for non-adaptive learners. And then if we look at estimation under samples, then you get something in between. So you get both an upper bound and a matching lower bound, which is about square root of n over epsilon. So this is the samples that you need to estimate the function. Now, the way I set it up is f is an arbitrary real valued function, so you need to make some assumption to make this problem reasonable, because one reason why f might be hard to learn is that, or to estimate, is that maybe there is one value at which it takes some unusually large, some one input in which it takes some unusually large values. So you need some assumption on that it has to be nice. So for the upper bounds, we assume that the function has to have bounded for norm. And I don't know if this is kind of the best assumption you can make. Maybe you can make a slightly better assumption, but something somewhat open. But the lower bounds hold even for Boolean valued functions. So an f that just takes plus minus 1 values. Okay. So that's what I want to talk about.
Not known before. Query model.
Well, that's why I like to give it in front of experts, because maybe they will tell me they were known. But I didn't know before. It hasn't. So I will tell you what was known and what people have studied before, but I don't think they have studied this particular thing.
Can I ask just one question about the learning results? This is for learning a linear function or a function that's epsilon close to linear?
A function that is an epsilon approximation. Yes.
So any
to the best possible
function,
linear.
You want to be with an
yes,
epsilon.
An epsilon approximation to the best possible linear approximation.
Good.
Yes. Yes.
Yeah, everything assumes the data is right.
Right in what sense?
Well, when you've got real data, you're likely to have wrong values and real outliers.
Well, I mean, that's embedded in the definition of the problem, right? Because, right, so outliers, that's why you assume the norm boundedness assumption. If you have, right, if you have huge outliers, then there is no guarantee.
The outliers are gone.
Right,
Fine.
right. Good question. Okay. Yeah, so what is known, right? So like in in the sublinear algorithms community, like this is it's about linear approximation. So linearity is kind of studied to death, and in kind of the sublinear time approximation or property testing community, like the first thing that comes to mind is linearity testing. So what is the linearity testing problem? Is that I have kind of some oracle access to a function, and then I want to know if the function is exactly linear or if it's far from linear in some sense. And this has been studied, like it has many motivations, and usually it has been studied in this kind of intolerant testing where you just want to know whether the function is exactly linear or it's somewhat far from a linear function. And when you define it like that in this setting, like how you measure the distance to linearity is not really so relevant. And in fact, you can think about it in terms of Hamming distance. And that's usually how the problem is set up. Because if the function is exactly linear, if I test it at any points, I'm going to see an exact linear function, and I don't have to worry about error. If I see something else, well, it has to deviate from the linear function, so I can say, well, at how many points it has to deviate. So like and there is a bunch of tests that have been designed for this, right? The first linearity test you might think of is like the Blum-Luby-Rubinfeld test. And that one is okay, it works for functions that have a range over, say, Boolean values, GF2, or in general functions whose range is in some kind of, like maybe, it could be even a non-abelian group, but it has to be some kind of compact group. When the function is real valued, I only know of two such results, and maybe you can tell me more. So one is this test, which was actually, it's a very nice test for linearity, and more generally, it's a test that tells you whether, if I have a function of many variables, if I can write it as a direct sum, as a function of x1 plus some function of x2 plus some function of x3, and so on. Right, and in particular, when the function is over the Boolean cube, this reduces to linearity testing. And the nice thing is it doesn't matter sort of what the range of this function is. It always works. And the way that this test works is that I'm going to take sort of two inputs. I'm going to call it xy. So you can think of xy as a partition of like an n-bit string into x bits and y bits. Right, and I'm going to take another point, which is x prime y prime under the same partition. And then I'm going to compare the value at xy and x prime y prime with the value at x y prime and x prime y. And then if the function is linear, everything should cancel out and you get 0. And it turns out that if like you do this partition randomly, and then this is a good test that tells you whether the function is linear or it's far from linear. So this test works quite well, like in the intolerant regime. And my first open question is something that I don't know the answer to, is that whether it gives you any guarantee when you're in this kind of tolerant regime, where I don't want to know if the function is exactly linear or not. I just want to know kind of how close it is to linear. One natural way to convert like an intolerant tester into a tolerant tester is that I just take the difference of the left-hand side and the right-hand side square, say, and I can say maybe that's some proxy for the error of the test. For this specific tester, I don't know like if anything can be said about it. There is another one which is like specifically designed. This is for functions that are not over the Boolean cube, but they're over Gaussian inputs. So it's a similar problem. So the x and y now are like take values like in their standard n dimensional, say, Gaussian vectors. And this was, I think, first proposed by Koch and Moskowitz, and this is the way the test works. It's a bit like the linearity test of VLR, but you have to kind of scale things to make the distributions right. So instead of f of x plus f of y equals f of x plus y, what you do is you add in the square root of two factors, and then everything works out. And this tests linearity over Gaussians. And then there is some extension that by Fleming and Yoshida, where they took this tester and they actually showed that it can be used as a basis of a tester for arbitrary distributions. So not only for Gaussians, but you can add some kind of checks to it, and then it tests whether a function is exactly linear or far from linear under arbitrary input distributions. So it turns out that this tester kind of also tells you a little bit about the distance to linearity, in the sense that if I look at the difference of the left-hand side and the right-hand side squared, it's like somehow it gives you some approximation of how close you are to a linear function, but it's not a very good approximation. It's like some constant factor approximation. But it's a little bit closer to where we're going. Like it's a little bit more in the right direction. So yeah, so given like what was studied and what I know, like these are the only works I know about this question before. Okay, so
question.
Yes.
What is the expectation of the difference of these? Does it have any connection to, like, if they're not linear and you look at x and y?
Yeah, so we'll get to it. I'll show you what it is. I'm going to analyze it over the Boolean, like something over the Boolean cube, but you'll get a sense, right? It turns out that there is something that you can relate. Good. Okay, so let me sort of see, and that's exactly to build up on your question. So how can we analyze? Like, what can we tell about the difference between f and the closest linear function? And like the way that I set up the problem is that it's very natural to use like orthogonal decomposition to try to study this question. So what is orthogonal decomposition? It says that I can actually do, like, I can write any function as a polynomial, right? As a multilinear polynomial if I'm working over the Boolean cube. And then I can kind of
Zoom, the slides have disappeared.
Depending on degree. So f0 will be the degree 0 part, that's just a constant, that's the bias. F1 will be the linear part, that's the part that we're interested in. And then there are the higher degree parts of the function, right? So that's, I can decompose any function that I want in this way. And the nice thing about this decomposition is it's an orthogonal decomposition, so we can think about it geometrically. And what I'm going to do in this talk, I'm going to completely forget the bias part. It's not relevant. I'm going to assume that the function that I'm interested in is unbiased, so the bias part disappears. It's easy to handle it, so we can just pretend it doesn't exist. And if the bias part doesn't exist, then this is the picture, is that f1, the linear part, is just the orthogonal projection of the function f on the subspace of linear functions. And what is the distance to linearity? Like, it's the square difference between f and its orthogonal projection. And because of orthogonality, it's just the difference of the squares. So estimating the square distance to linearity is essentially the same problem as estimating the square of the projection to the space of linear functions. Right? I also have to estimate the square norm of f, but that's where these boundedness assumptions help. Like this I can do using like 1 over epsilon squared queries, so it doesn't affect the query complexity altogether. So this is really what we're interested in, is what happens in the direction of the linear functions. Okay? So like there is a finer decomposition, and that's a Fourier decomposition, right, which tells us that the linear part
on Zoom, the slides have disappeared.
as like the coefficients are the Fourier coefficients, right? It's a linear function, and the Fourier coefficients themselves are.
Hello?
Or say that they can see the slides.
They cannot see the slides. This should fix it. Sorry about that. Right. So it's good now. Okay. So Right, so the coefficients themselves can be estimated as the correlations between the function and the different coordinates. So that's something that you can estimate given enough samples, right? Well, how many samples do you need? Well, to estimate this with like error, like, I don't know, epsilon, let's say you need something like 1/epsilon² samples. So you can in fact estimate the individual coefficients if you wanted to, like that's one way to get the linear approximation, right? I can get estimates for the squares of each one of the individual coefficients, and then I can add up these estimates to get an estimate for the square projection in the one direction. And that's essentially what the LMN algorithm does. That's what linear Mansur and Nissan does. And if you calculate it, you need to get the total error to be epsilon, you need to have roughly epsilon/n error for each coefficient. So you need a total of something like n/epsilon samples. Like there is a square here that makes n/epsilon be the right number and not. So that's, but this does too much in some sense. This gives us not only an approximation, it actually learns the function, because if we know the coefficients with good enough quality, then we have actually learned a good approximation to the function. So how do we improve on this? So here is like the first way that we can improve on it, just using samples. Like this doesn't require queries to the function, and that's that. We can take this expression, we can look at, what is it? Like the sum of the squares of, did I cheat here? No, I didn't cheat. So anyway, you can rewrite this expression. So good, right? So that's the correlation of f with the closest linear function squared, and you use this trick where you split. You think so. This is for a randomly sampled x, and if you square this expression, you can like replace this random choice of x with two independent choices, x and y. That's something that the physicists call the replica method. So I take like two copies like of the same random variable, and then when you simplify the expression, you get something of this form. And I cannot think of my feet, and I don't know if I made a mistake in what I wrote here, but this is the expression you get at the end in any case. And this gives you a way to estimate the square of the function. And so why is this advantageous? The reason that this is advantageous is because now it's an expression that's f of x times f of y times the dot product of x and y. And now, let's say if I have 3 samples, I can estimate this quantity by doing an empirical average of f of x1, f of x2, x1, x2, f of x2, f of x3, x2, x3, f of x1, f of x3, x1, x3. So if I have, let's say, k samples, then I can write this as an empirical average of k² values. And that effectively kind of reduces my sample complexity from n to square root of n, because I can use information about the pairwise dependencies between these samples. And these are not going to be completely independent of one another, but it turns out that the covariances are small enough that it still gives you the correct estimate. So does that make sense? So that's kind of like one way to save a factor of square root of n when you do estimation instead of learning. And that turns out to be optimal if you only use samples, if you don't use queries. So what I want to show you now is like what I find the more surprising result is that if I allow query access to the function, then I can do a query complexity which is completely independent of n, the dimension. And yes.
I mean, both the analysis and the algorithm looks like uniformity testing from a distribution here. Is there a connection?
Uniformity testing from a distribution?
Like if I give you this option, is it uniform or not?
I see.
You get like with sample access from it. You can do it with root n over epsilon sample.
I see, it's the same query complexity.
Like the same sample. I mean, the problems are
the same sample,
but the analysis.
The analysis is the same. So you're saying that maybe in this guise you're testing for the uniformity
It's
of
there a
the
connection? Yeah.
I don't know. Yeah. Maybe there is. Maybe right. It's a very good question. Yeah, I don't know. Yeah. So maybe you're doing something in this guise, which is not. Yeah. So now what happens if you get query access to the function? So then it turns out that there is another tool that is very useful for figuring out what is happening. And the main idea is that you can, again, like if you look at the orthogonal decomposition of the function in terms of like degree 1 terms, degree 2 terms, degree 3 terms, there is this way to kind of dampen the contribution of each successive degree term by adding some noise to the function. So how does this work? Well, if instead of looking at the function itself, I average out the function. So this is the noise operator by taking each bit of the function and flipping its value with some very large probability. So what is this very large probability? This is rho, that's the bias of the noise. So each input bit x1, somehow with most of the probability, I flip the value and replace it with a random bit. And with some small probability rho, I preserve the original value. And that's the notion of the rho bias noise. So then I'm going to change the input. And it turns out that the average value of this new like noisy function is given by like the same expansion, but then with this dampening factor of rho in the term. So like the first level, like the linear part is going to be multiplied by rho, and the square part is going to be multiplied by rho squared, and so on. So what can we do? So what this tells us is that now if I measure like the norm squared of this like noised up function, it's also going to be a real valued function. It's going to be like rho squared times times the linear part, and like the other part, like the f squared, f cubed part, and so on, they only participate, but they only participate with the contribution of rho squared. So when I square that, they give me a rho to the fourth. And that's kind of like the key reason why you can get a very good estimate of the linear part, is because now if I try to estimate like the function hit by noise by doing an average estimate, like an empirical estimate of the terms, right? I get two sources of error. I get a systematic error of the order of rho to the fourth, and then I get some random error based on the fact that I'm estimating an actual value using samples. But that's kind of the formula, right? Is that now I can average out these values, f of x times f of x, like hit by some noise, right? And if I average out enough of those values, I get a good approximation of the right-hand side here. And the right-hand side is this one norm of the function kind of dampened by these rho squared factors, plus minus some lower order term. Okay, and I know you can kind of try to calculate what you need, right? So if I want to get an epsilon approximation of the function, then I want the systematic error term to be on the order of epsilon, right? Because I want an epsilon approximation on the whole function, right? So what I did here, I divided up by this noise parameter rho. So I want it to be epsilon. I want the systematic error to be about epsilon, which means that now I need to have enough of these samples to average out, so that even when I divide by epsilon, I get another approximation whose quality is epsilon. Okay, so I need essentially an approximation of quality epsilon squared for this average. And to get an approximation of quality epsilon squared for the average, I need 1 over epsilon to the fourth terms. Okay, and that falls short of what I promised you, but that explains why you don't need a dependence on n. You can get something which is completely independent of the dimension. And I don't know, when I saw this, I thought it was a little bit surprising that you can do that with something that doesn't depend on the connection. Is there a connection with uniformity testing here, or some similar phenomenon that happens there, or? Not sure. Okay, so, okay. But I guess the query model there maybe is not so natural to study. This is query complexity. So why is this query complexity? Because we need to average this f of x times f of x hit by noise. And these are now not independent anymore. So they're actually these row correlated pairs of inputs where I take two Boolean strings that are not independent, but they're kind of noisy versions of one another. Right? They're not completely independent. But the noise rate is quite large, so they're kind of almost independent, but not quite. But you do need queries in order to be able to simulate this kind of access. Okay, so that's sort of how we get something which does not depend on n. We get sample complexity 1 over epsilon to the 4th. How do we go down to beyond that? And I mean, I come from complexity. So when I see a problem, I want to prove a lower bound, right? So when I saw this, it's like, come on, there must be a lower bound of 1 over epsilon to the 4th here, right? There is no way you can do better. Like, because, you know, just if I want to estimate like the mean of a function, I already need 1 over epsilon squared queries, right? So surely estimating like the whole linear part should require more effort than estimating the mean. So I was there and I had a postdoc at that time, Gautam Prakriya, and I told him, you know, prove a lower bound, and he couldn't prove the lower bound, and I was unhappy, and we didn't get anywhere. And then Lorenzo, who was my co-author on this project, came to do a project with me like last year at some point, and he was like, what am I supposed to do? And I was like, well, you know, you can try your hand out at this problem if you want, but I don't recommend it because, you know, we've been thinking about it and we got stuck. And like a few days later, he said, I know how to improve it to 1 over epsilon cubed. Okay, so let's see how you are going to improve it to 1 over epsilon cubed. And this is how you're going to improve it to 1 over epsilon cubed. So his idea was that, well, I can apply noise to the function f, and this is the expansion I get when I apply noise. This is like positively correlated noise with rate rho, but I can also apply negatively correlated noise with rate rho. So I can make like x, you know, the bits be push away from each other, right? Negatively correlated. And the expression you get for negatively correlated rho is like the same, but with the signs flipped. Like it's minus rho squared minus rho cubed and so on. And now what do you do? Well, I have two equations, right? I want to solve for f1. So what I'm going to do is I'm going to subtract the two equations, and I'm going to get something which has like the part I care, which is the linear part with the rho coefficient in front of it. But now the quadratic part is going to cancel out completely. And then kind of the rest of the noise I get is on the order not of rho squared, but is going to be on or the order of rho cubed. Okay, so that was the idea and it works, right? So now I can write, I can now write an unbiased estimator for this function here, right? Because what do? I kind of just average the unbiased estimator for a rho correlated pair x and y, and the minus rho correlated pair x and y with the proper coefficients which make things cancel out, right? And I know that this is an unbiased estimator, so if I take enough samples of it, I should be able to get a good approximation of that. And the gain that you get is now, like instead of getting rho squared here, you get a rho to the 4th here. So you're going to need fewer samples. And if you do the calculation, like it turns out that you're going to only need now 1 over epsilon cubed samples, like for this estimator, like a properly scaled to give a good approximation. Well, now that you go all the way down to 1 over epsilon cubed, now you get greedy and you see how far can you go. And to see how far we can go, it helps to think about this problem more systematically, right? So here what we did is somehow we hooked up a cancellation in the noises so that like the part that we like survives, but all of the other parts cancel out. Well, this is only one way to hook up a cancellation. I can try to find other ways to hook up cancellations. So here is sort of a generic way in which I can try to hook up cancellations that give me what I want. I can say, well, I'm going to try a noise of rate alpha times rho, and then I'm going to try a noise of rate beta times rho, where alpha and beta are just some unknowns that I'm going to solve for later, right? And then these are the equations I get for what the noise, the functions hit by noise are going to look like. And now what I'm going to say is that if I scale the first equation by A and the second equation by B, I'm going to get something. Well, I want the first part to survive, so I want alpha A plus beta B to be 1. I want the second part to cancel out, right? So I want alpha squared A plus beta squared B to be 0. And then I kind of want to, like, I get something which is order of rho cubed, which is the contribution of the third and higher parts, right? So I had when I was in graduate school, I had the student who studied with me was Greek, and he was always bothered that when you use A and alpha for different symbols, because he says it's the same, A and alpha are the same, so you shouldn't use them for different symbols. But I'm going to use it here. There is A alpha and B beta is 1, and A alpha squared plus B beta squared is 0. And right, and now you can say, well, actually, any way that I solve this equation should work. It should give me the cancellation that I want. So one way in which we solved it is like if I said alpha is 1 and beta is -1, that's like using noise rates rho and minus rho. But here is a completely different solution. I could have used alpha equals 1 and beta equals 1 over 10, let's say, and then A and B would solve to -1 over 9 and 100 over 9, and that's also a solution. Now, which one of these two solutions do you think is better? Like, they both work. They're both going to give me an algorithm of query complexity 1 over epsilon cubed. But I claim, like, in some sense, if I had to implement this algorithm, one of these would work better than the other.
The second one, because you get 1 over 1000 in front of PQ, or? You
will, but you have to pay a price for it. Okay, so you will get 1 over 1000, but you have to pay a price for it. So it's actually this one that's better than the two. And the reason it's better is because this coefficient becomes very large. This B becomes very large. So when you're doing the sampling, right, you're averaging out somehow scale values by these functions. And if I use huge coefficients, then I have to pay for it in the variance of the sample, right? So I really want to use numbers which are as small as possible for the coefficients to make this efficient. So now we kind of know what we're aiming to get, and now I can move from, like, I mean, this was just like alpha and beta, but now I can also use gamma and delta and so on and try to get more cancellations out of the way. So the general model, like, we can kind of think about it this way, is that what I'm really trying to do is I'm trying to minimize this vector of coefficients A, comma B, dot, 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 comma C, right? I have a bunch of them. And I'm setting up these equations where the first one is, right, this is the linear part, this like survives, and all the parts from degree 2 to degree D are going to vanish, and I want to pick these coefficients to be as small as possible, right? And what are these alpha, beta, gamma? Well, there are some like multiples of the noise rate, so there are some numbers between -1 and 1. So can you expect to do this? And in fact, how small can we expect to get these coefficients to have a system of equations like this, to solve a system of equations like this? You get a van der Waals matrix, exactly, right? So kind of as a first approximation, right, I can say, let me ignore the right-hand side here completely, right? And this is a van der Waals system of equations. And really what I care is about the smallest singular value of this system, right? Because I want to say, well, if I wanted to argue that, you know, like I get solutions of small norm, it means that like whatever I put on the right-hand side, I want to say that the inverse matrix does not grow it by too much, right? So what do you think? If I write a van der Waals matrix like this, is it going to be, here I cheated a bit, I added an all ones row, but it doesn't make a difference. It's just for things for van der Waals. What do you think? Like, what is the singular value of this matrix? How is it going to grow with the dimension? No. Exponential. Okay, so it's going to grow inverse exponentially in D. And there is a beautiful proof of this. And it's something like that you don't see. Like, I guess it's so obvious to people who do that. I never found the way it's written down. But it's a one picture proof. So I'm going to show you the picture. It's a proof by picture. And this is the picture. It's the Chebyshev polynomials. Okay, it's a proof by picture. So how is it a proof by picture? What are the Chebyshev polynomials? They are this magical family of polynomials, right? This is what they are. But when you look at what they evaluate to when the input is between -1 and 1, the value is also bounded between -1 and 1. And I claim that this proves that the singular value of this matrix has to be large. Or like the smallest singular value has to be very small. It's 2 to the minus d or something like that. Why? Well, if I hit this matrix by some vector on the left, right, I hit it by some vector of the left, what happens? It's polynomial evaluation, right? The polynomial multiplied by a column vector here is like, these are the coefficients of a polynomial, right? So I can think of this as being the coefficients of a polynomial, and this is going to be the value of the polynomial, right? This is going to be P of alpha, P of beta, P of gamma. But the Chebyshev polynomials, like say the large Chebyshev polynomials, are a witness that you can take something which has very large norms, like the coefficients grow 1, 2, 4, 8. So TD will have coefficient 2 to the D, right? It's something of very large norm. But when you map it, it's always going to evaluate to values between -1 and 1. It doesn't matter how you pick the roots, right? These alphas, betas, and gammas, like no matter where I put them, alpha, beta, gamma, I know that whatever I get on the right-hand side are going to be some values in the range between ±1 and 1. So the Chebyshev polynomial is actually a witness. It's a very large vector that when I apply any van der Waals matrix to it, is going to map to something very small. Okay? So this is kind of bad news. It tells you that this matrix like has actually, it can shrink vectors by a lot. So in general, I cannot guarantee anything about it having a short magnitude. But in fact, it turns out that like this is one of the kind of things with Chebyshev polynomials, is that they show you that something is impossible, and then at the same time, they tell you how to do it. Okay? And here we are said, well, actually, the way that we modeled this problem was not quite the whole story, because we said, if I look at this matrix of values, like what's the worst case, and what is the most by which it can shrink the input? But actually, here I have a specific output that I want to get, which is this vector 1, 0, comma, 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 0. It turns out that for this specific output, you can do much better. Why can you do much better? Because of Chebyshev polynomials. Okay, so this is the other picture of Chebyshev polynomials. So this is like what they are. It's not super important for what we do, but it turns out that what the Chebyshev polynomials are, they're actually like the Fourier basis, but not Fourier basis over the Boolean cube, Fourier basis over the unit circle, but then you project it like to the real axis by doing this kind of, you replace e to the I theta, which is like the input, with the real part, and then it becomes the cosine of something, and then you get this beautiful relation that the Chebyshev polynomial at cosine theta is cosine of n times theta. So that's their defining property, and that's why they look like this. So the important part for us is like, this is not so important, is that Fourier basis, it's nice because of orthogonality, and it turns out that the Chebyshev polynomials inherit the orthogonality. It just looks a little bit different. They're orthogonal, but not with respect to a uniformly chosen input, but with respect to an input which is a cosine of a random angle, right? And then they're orthogonal with respect to this input. And just like the usual Fourier transform has a discrete Fourier transform variant, like the Chebyshev polynomials have a discrete variant. And what the discrete variant tells you is that if I take the first d polynomials, they're also orthogonal with respect to this discrete product. So what is this discrete product? It means that now I take a summation where f and g are evaluated at some specific subset of points, and then the first, the second, the third, up to the d polynomial are going to be orthogonal with respect to this. What are these points? Well, they're what are called the Chebyshev nodes, and that's what they look like. They're these points that are uniformly spaced around the circle, and then I project it down to like the ±1, so I get alpha, beta, and gamma. So that's what my alpha, beta, and gamma are going to be. They're the cosines of pi 2i - 1 divided by 2d, whatever, right? That's the formula that you get. So I still find this kind of magical, like I don't know what is happening, but it works really well. So how does it work? How do we use this orthogonality? Well, now we can rewrite this whole system of equations in the basis of Chebyshev polynomial. So remember, these equations are just equations about polynomials, right? So I can say that this kind of, so what is it? A alpha squared, A alpha to the D, right? If I hit this on the left-hand side by some coefficients, I get some polynomial equation, right? Sorry, this AB comma C, I can think of it as a polynomial, right? Good. Right, and these are just orthogonality relations for the Chebyshev polynomials. Like the first equation tells me that A, B, and C are orthogonal to the first Chebyshev polynomial. The second one tells me that they're orthogonal to the second Chebyshev polynomial, and so on. And now, once you write out the equations in this form, then, am I cheating here? Maybe I'm cheating a little bit, but it's essentially true. So once you write the equations in this form, right, once you write them in terms of the Chebyshev polynomials, like the solution comes out staring at you. Now I want the short p that satisfies all these vectors. So what am I, all these constraints? I'm just going to pick this short p to be the Chebyshev polynomial, the first Chebyshev polynomial. So I get that it's the identity function. And now it turns out that the solution is actually A equals alpha, B equals beta, so I didn't cheat. Right? They actually do represent the exact same symbol. Right? So that's the outcome, is that you do end up getting with the short solution. And so what is the algorithm? So the algorithm is, now it comes out of this. It's like this is how you estimate the distance to linearity. So essentially what you want to do is you want to take kind of this combination of f of x, f of y, but now x and y, the correlation between x and y itself is some combination of like rates, like that are multiples of the Chebyshev nodes. So like when you write the whole down, write down the whole thing, this is what it looks like. Right, I'm going to have these different, what are these? These are the Chebyshev nodes, right? So I'm going to sample the I Chebyshev node with probability proportional to its magnitude. And then I'm going to sample a correlated pair x and y, where the noise now depends on this alpha I. So there's some base noise rate rho, but now I scale it down by Chebyshev node. And then I have like, the estimator does something very simple, right? It has some scaling factor, which is not too important, but essentially what it does is it just outputs f of x, f of y, where x and y are now rho alpha I correlated random variables, right? They're this x and y from here. Right? And I mean, this backs up like things a little bit more, like to get something whose rate is as good as it can be. So before that, what we wrote it is we had kind of a linear combination of these terms, f of x, f of y, f of x1, f of y1 with one rate, f of x2, f of y2 with some other rate, and so on. But I can like just sample x and y from randomly from these rates, and then I can write down the whole estimator like this. And then if you plug in the right parameters, now it turns out that these four parameters is going to scale as epsilon to the 1 over d, and then you get this estimator of this 1 over epsilon squared times slope cube 1 over epsilon complexity. Yeah. Yeah. So that's so that's what I wanted to say, right? That's kind of. I was quite a bit surprised of this result. Why I think it's surprising? As I said, because 1 over epsilon squared is something that you have to pay, even if I want to just get like a single Fourier coefficient. If I just want to get the mean squared of the function, then I have to pay 1 over epsilon squared. Here we say like I pay a tiny bit more, and now I get something that depends like on n different numbers, like on the first level approximation. So now you can get even more greedy, and you can ask, well, can I even remove this slope cubed from here? And I don't know the answer to this, and I find it to be a fascinating question. These are a few things that I can say about it, is that this specific method cannot improve it beyond log squared 1 over epsilon squared. Why? Again, because of Chebyshev polynomials, because like this is kind of where you hit the limit. And the fact that like you cannot pick something which is much shorter than what you cannot pick this AB dot C vector, which is much shorter than what I told you. And that kind of imposes the limit for this particular method, or at least about the way that you analyze it. But I don't know, like I don't have a lower bound that shows that the polylog is necessary. Maybe I'll say a few words about it. So one way I thought about maybe getting some insight on this is to say, well, no, actually there is very little you use about approximating the linear part in this method, and you can say, well, can I approximate the degree 2 part or the degree 3 part of a function? And the answer is yes, you can, with the same complexity, but now you pay a log that raises that, like whose power depends on d, right? And somehow this tells you that maybe this factor becomes more important when you look at larger degrees. So maybe that can help us explain things. Let's say if I want to approximate the degree d part of a function, how many queries do I need to make to the function? And now let's think of d as not being 1, but let's think of it as a very large number, maybe something that goes to n. And I don't know any lower bound for this. Like the only lower bound is like seminal work of Eric with Josh Brody and Kevin Matulev, where they showed that d queries are necessary for learning a linear function, or for testing like whether a linear function depends on d inputs or d plus 1 inputs. That's the only example I know. So there is a big gap there that I don't know about, and I'd be interested in knowing more about it. Yeah, but that's the state of my knowledge about this question. Yeah, you know what? I think I'm going to stop here. This took more time than I thought. I was going to show you like the 1/epsilon² lower bound and why I don't know how to extend it, but I think I'll leave it at this and maybe take some questions.